CMSC 203 Computer Systems and Organizations Quiz 1, submitted by Myra Matsushita. So the first lesson in Module 1 is Representation of Information. So programs are sets of instructions that a computer runs to manipulate data, and this data can be represented using different systems, such as the binary system, which is used by computers, and the decimal system, which is used by humans. So for these data, we use bits, which are comprised of a sequence of binary digits that has a distinction between two possible states to represent this data. These data are stored in a specific memory address, and they can also be grouped. For example, a group of 8 bits forms a byte, and a group in groups of 16, 32, or 64 bits form words. For bits and their values, we can use the below rules to remember that a set of n bits can take on any 2n values, and that to represent n values we need log n bits, where the parentheses indicate a rounding up to the next integral value. So we also have different number systems, and for the conversion from these number systems for decimal to binary conversion, we can divide the number repeatedly by 2 and simply take the remainder as is in the example. For binary to hexadecimal conversion, we group the binary digits into a group of 4 digits starting from the right, adding zeros at the left if there are no exact 4 digits in the leftmost group, and convert each group of 4 bits into hexadecimal. Lastly, for binary to decimal conversion, we do this by simply multiplying the digit with its place value and then adding all the results. So in binary, the rightmost digit has a place value of 20, the next rightmost has a place value of 21, the next 22, and so on. So to illustrate this, please see the below example. For the representation of integers, we have a concept called complements, which are used to represent negative integers, and these have two types: the ones complements and the twos complements. Most computers use twos complement of a number, where each bit is reversed and then 1 is added to the result. So we can also conduct arithmetic operations using integers. For example, in addition, the leftmost bit is disregarded. If the result of an addition is too large in magnitude, the sign will be interpreted incorrectly, and this is called an overflow, which you can see to the right. We can also conduct subtraction using integers. For the representation of real numbers are represented using coefficient, or also called mantissa, and exponent, which are made unique by nominalization. We also have a process called exponent biasing for components, where exponents are biased to represent both negative and positive exponents by complementing their leftmost bit. The process of normalization that we also mentioned a while ago refers to normalized coefficients, which are coefficients with large magnitudes and exponents adjusted to maintain the value of the number to make real numbers as accurate as possible. We also have a concept of a hidden bit, which is a coefficient that is assumed to be 1 but is not stored explicitly, so we cannot find it anywhere. Lastly, we can also conduct arithmetic with real numbers. So we do this first by unpacking the exponent and coefficient registers, then conducting the arithmetic operation, and afterwards, for the final result, we will again pack together these two. For example, for addition, we align the radix points, we add the coefficients, we renormalize the results, and then we pack them again. For multiplication, we first add the exponents, then we multiply the coefficients, we renormalize the results, and we conduct packing again. So this is a sample of the representation for characters. So characters are represented using n-bit unsigned integers, and the ASCII character set is most commonly used, with its first 32 characters being called control characters and the other characters being called fixed characters. We also have a representation system for programs. So before we talk about the representation system, we first need to discuss what instructions are. Instructions comprise a program stored in memory and when encoded to binary are called machine code or language. So you can see in the left side the basic instruction codes that are commonly used. For programs, programs are represented by a sequence of instruction codes, which we discussed in the previous slide, which begins with an operation code followed by operands, as you can also see in the sample. For the next module, it will be about digital electronics and Boolean algebra. So digital system represents information in a discrete form while analog system represents them in a continuous form. So these are the mainly used systems to represent electric signals. So we also have a concept of four logic levels, which are the range of acceptable voltages for one state or logic level, and voltage that falls outside these levels are commonly undefined. Positive logic uses low logic level as 0 and high logic level as 1, while negative logic follows opposite convention. So these sample of the logic level thresholds, with low being 0 to 0.7 or 0.8 and high being around 2.7 to 5 volts. We also have combinatorial logic. So a combinatorial circuit has outputs which depends on its inputs and is independent of the past history of its inputs. So we have logic gates that perform logical manipulations on one or more logic levels with four main types. So these are inverter, AND gate, OR gate, and exclusive OR gate. So the inverter is a device which changes a low logic level to a high level and vice versa. So it's similar to NOT. An AND gate is a two-input device with one output which is high only when both the inputs are high. The OR gate is a two-input device with one output which is high if either or both the inputs are high. Lastly, we have the exclusive OR gate, which is a two-input device with one output which is high if either input is high but not both. So you can also see other examples of the logic gates aside from the ones discussed, such as NAND and XOR. So for the circuits of addition of circuits A and B to give sum S and carry C can be done. So there are mainly two types. Half adders produces sum bit and carry bit and does not allow carry from previous stages, as you can see here. So it will only definitely use the data inputted. While there are also the concept of full adders, which accepts inputs from AI, BI, CI1 to produce SI and carry CI. So as you can see, the data is carried over for full adders. So full adders adds one bit position within an integer. To add this integer, we can use two types of circuits. So a parallel circuit here on the right contains n separate full adders with carries appropriately linked or cascaded. And we can also use a serial circuit with the single adder circuit where the bits of the two integers are fed sequentially into the circuit and the carry output is delayed and fed to the carry input for the next stage. Another type of logic is the sequential logic. So this is when the behavior depends not only on inputs but also on data stored inside the circuit. So we have different types of sequential logic circuit, such as clocks, which are devices with no inputs and an output that changes from one logic level to another. Flip-flops, which are devices that has two different states with various types on how the states are changed. Registers, which are sets of flip-flops treated as a single unit all loaded and sensed at the same time. Counters, which are registers with logics attached to to make it count in binary. And shift register, which are registers with logics attached so that logic can be sampled one bit at a time. So for the next portion of this module, we're going to be discussing Boolean algebra. So what is Boolean algebra? Boolean algebra is the mathematics of two-valued logic in which one of the only two possible values can be used by the variable. So Boolean algebra has its own postulates and fundamental theorems. Some examples of these would be identities, idempotency, complements, commutativity, associativity, distributivity, De Morgan's law, and more. It also has its laws, such as the laws of identity, commutative laws, associative laws, distributive laws, absorption laws, expansion laws, and De Morgan's laws. Aside from this, we also have common identities used in Boolean algebra, which we derive from the previously discussed laws and theorems. After this, we're going to be discussing logic expressions and logic circuits. So any logic expression can be mapped as a logic circuit, as you can see in the example below. For the third module, we're going to be discussing computer systems organization. So the first thing that we're going to discuss for computer systems organization are processors. So processors, which are also called central processing units, perform logical, arithmetic, and shift operations demanded by the computer's instruction sets. So this is mainly composed of three main parts, which is the arithmetic logic unit, which performs the arithmetic, logical, and shift operations, the register set, which has general purpose registers and special purpose registers, and the control unit, which is used to control the machine cycle. So we have two types of control units mainly, microprogrammed and conventional. The microprogrammed control units have control signals which are stored in an internal memory called the control store. As for conventional control units, the control mechanism is a combinatorial circuit which simply decodes its inputs and produces the appropriate set of control signals for each step. For the execution of instructions, the machine cycle mainly consists of fetching instruction from memory, then decoding the steps, and finally executing the micro instructions. So as you can also see in this program here, so we fetch the instructions from the CPU, we decode this into language that the CPU can understand, and then this will be executed afterwards. So computer also have their own memories aside from humans. So memories are part of computer systems where programs and data are stored. The basic unit of memory for binary digits or the computer is a bit. So bit memory comprises of the basic unit of memory, which are composed of a number of cells which can hold information. So this is a sample of a 1-bit memory. So for the cells that we mentioned a while ago, the cell size equal to a byte is called byte addressable, and cell size equal to a word is word addressable. For types of memories, we have the random access memory, which we call RAM, and the read-only memory, which is usually called the ROM. Random access memory is a memory where any location can be accessed for a read and write operation for a fixed time, while read-only memory is a memory whose contents are permanently fixed and remain valid even with no power. So aside from the previously discussed memory types, we also have something called a memory cache, which helps reduce the time required for the processor to access memory storages. The memory cache are sets of memory registers which contains data most likely to be copied in the near future, with a 90% estimated memory access found in cache. So we usually hear these words when we are referring to browsers. So aside from these, we also have other types of memories such as magnetic disks, optical memories, and other secondary memories like magnetic drums. For the next concept, or vital component of our computer system, we also have the input-output system. So you can see here, which we all learned during our computer classes. So input-output systems include both physical input-output devices, such as keyboards, printers, and video displays, and it also includes interface devices. So these parts are used by humans to communicate with the computer and for computers to communicate its responses to humans. So some examples of this are switches and lights, which can be found in keyboards. So we also have video displays. So in this case, maybe on a headset. And there are also two types of displays: a character display, where a stream of character codes is sent to display, and a bitmap graphics display, such as the monitor that we're referring to here, where a large section of memory is dedicated to representing the display. So display is mainly broken up into dots or pixels, with one bit representing each dot. Aside from this, we also have cursor tracking devices like the mouse and the printers here. So aside from the input and output system, we also have something that are called computer buses, which are a set of wires or lines to which components of the computer are connected. So these has four main types. The first being the data bus, which carries data from one component to the other. The next one is the address bus, which carries addresses which determine memory space. There's also something called the control bus, which carries signals which coordinate the components of the computer. And lastly, we have the power bus, which carries with it power at various voltages to the different components of the computer to ensure that they are going to be working correctly. So for the operation of the buses, in the processor, there's usually a bus master that can initiate activity by identifying the transmitters or the device that will put the information on the data bus, and the receivers, which are the devices that will read the information from the data bus. Aside from the bus masters, the other components are referred to as the slaves. So bus operation also includes bus addressing, where the devices attached to the buses are identified by addresses. And by using addressing, we use this to recognize any address in the range in which components should move. And these are also decoded through a process called address decoding. So for the next topic, we're going to be discussing the essentials of assembly language programming. So for assembly language programming, this is the 80 by 86 assembly by Intel, which is currently considered as standards and is still being maintained using vertical compatibility even with its newer models. So this is the sample of the 80 by 86 architecture. So it is comprised of an arithmetic and logic unit, a control unit, general registers, several special purpose registers, and control and status flags. So the ALU, or the arithmetic and logic unit, is responsible for the arithmetic operations and relational comparisons, while the control unit coordinates the operations of the active parts of the CPU. So the control unit also has different parts, such as the bus unit, the instruction unit, the execution unit, and the address unit. Aside from this, we also have registers, which are used to store values when writing assembly language programs and has general and special purpose types. For example, we have the accumulator register, the base register, counter register, and data register for general registers, and for the special purpose registers, we have segment registers, pointer registers, and index registers. So for the next part, we are going to discuss operands. So these tell the assembler what registers, parameters, memory locations, and so on to associate with each instance of instruction or derivatives. For example, here in this picture, we can see we have two operands and the operator. So it tells that the operands are 1 and 2. For addressing modes, when using operands, we need to specify the memory location before using operands, and addressing modes help specify exactly which part of the memory will the instruction take effect. As you can see here. So for addressing modes, there are different methods of addressing them, such as immediate, where the operand itself is part of the opcode, absolute or direct, in which the address of the operand is given together with the opcode, register, in which the operand is stored in a register and that the register that contains the operand is in the opcode, register indirect, in which the address of the operand is stored in a register and the register is then used to locate the operand in the memory, relative, where there is a displacement or offset given together with the opcode, based, in which the address of the operand is obtained by adding a displacement from a register in direct mode, indexed, which is similar to the addressing mode, to the based addressing mode, but only index registers are used, and based index, which combines the addressing schemes of the based, index, and displacement to come up with the address of the operand. We also have string addressing, which utilizes the index registers SI and DI together with specific 80 by 86 string instructions. So assembly language programs use an ASM source code saved in a source file, which are then fed into assemblers to interpret this source code that transform these instead into an object file which the computer can then take an action on. So for the 80 by 86 instructions, 80 by 86 has a vast amount of instruction which we can see here in this instruction set. So for the instruction sets, they are mainly classified into 7 types: data transfer, arithmetic, logic and shifts, program control, string manipulation, input and output, and processor control instructions. So for example, for data transfer, we mainly have push, pop, for input and output, in and out, logic and shift, and or, sort, test, not, arithmetic, add, subtract, multiply, negate, program control, loop, processor control, wait, lock, branch conditions, sign, block and string manipulators, move, scan, load, string, and other instructions. For the next module, we'll be discussing assembly language programming constructs. So the first construct are sequences, which are a series of ASM statements that do not contain any instructions that alter the top to bottom sequence of executing instructions, so they are linear. The next one are selections, which consist of conditionals which allow testing of particular conditions while a program is running, and branching, where conditionals are evaluated and certain actions are taken, for example, to jump or to compare instructions. So choice before execution of one of the instructions. So we also have a concept of if then and if else, which is a sample of a forced jump, which is when the normal sequence in which instructions are executed changes. So for the case of if then, these are instructions to be followed if the condition is true, and if then else provide alternative actions for both true and false values of the instruction. So for if, we only provide what to do if it's true, and then for if then else, we provide conditions on what to do if it's true and if it's otherwise. So we also have a construct or concept of compound conditions, which arise when the conditional involves the evaluation of more than a single logical expression, and this usually mixes and or not. Another type is the case in which statements provide appropriate actions to be performed for specific value of a variable and may also have a catch-all else portion to do when the case is false. So another very important construct in programming is the iteration, which provides means to execute instructions more than once depending on some condition. So some samples of these are loops. So we have the for loop, first of all, which is executed when which is executed and terminates when a count is decremented to 0. You have the while loop, which the condition is evaluated before performing any statement in the loop. And lastly, we have the repeat until loop, which is used if the condition is evaluated at the end of the loop body. For the last topic, we have subroutines or procedures. So what are subroutines? Subroutines are well-grouped instructions that perform a relevant task with its most common form being a procedure. So we also have parameter passing schemes, which are programs that have particular group of instructions or subroutines that require certain data, which can also be referred to as parameters. For the parameter passing schemes, this is usually done by using registers, using memory variables, or using the stack, with using the stack being the most recommended form of parameter passing. We also have local variables, which are data values that exist only during the execution of a subroutine and are typically temporary. For example, here we can see the subroutine local variables. We also have functional return variables, which are functions are subroutines capable of returning values. So we have parameters, and after we add them, we have return values here. Lastly, we have recursions, which are subroutines that makes a call to itself, and both procedures and functions can be recursive. So it's just repeating itself. So that's all for this video. Thank you.